Hey everyone, welcome back to another session with OneClass. Today we're going to be going through some math problems at the high school and university level. My name is Bassam, I'm an engineering graduate, and we'll start off with the first question over here. Okay, so this question is asking us to circle to indicate whether each statement is true or false, and it gives us two statements. So I'm going to open up this image file to help us figure out what those statements are. So we'll save that over here and we'll open it up. Okay, so this is what we're asked. Circle to indicate whether each statement is true or false and justify your answer. So our first statement, if f at x is a differentiable function, then d at dx, so the derivative of f at square root of x, is f prime at x divided by 2 square root of x. So we need to verify if this is true, and then we'll go through the second problem as well. So we'll start off with writing out some givens. So we're trying to see if this statement is true for f at x when it's a differentiable function. So does this equal f prime at x, so the derivative of f at x divided by 2 square root x? And we'll put a question mark. Okay, so one way to think about this question is to kind of define f at x as some function. So let's say we defined f at x as x cubed, or it could really be anything. What we could do here is test out if the statement is true for, let's say, if we substitute, we know this is a differentiable function, so if we were to substitute f prime square root at x, would we get this as follows? So let me erase this. So we know f prime at x for this function will be 3x squared. And we know if we substitute for f prime square root at x, if we substitute that in, we'd get 3 square root at x squared, and this would give us 3x. So knowing this, we want to think about, let's say we looked at this equation over here. Can we use this to get the same values as we calculated here? So if we had the derivative of f, if we substitute f at x, so here, or square root x, so if we substitute f square root x, this would give us square root x cubed, which would be x 3 over 2. So this is one component, so this is the inside component over here. So using this equation down here, we know that the left side will be the derivative d dx of this function. So this is what we calculated. So we would just plug this in, so x 3 over 2. So x 3 over 2, does it equal, so we'll substitute in f prime at x, so 3x squared, and then we have divided by 2 square root x. So on the left side we would have 3 over 2x to the half, and then on the right side, if we multiply both top and bottom, so we'll multiply both top and bottom by square root x to get rid of the square root at the bottom. So, and this will give us 3x squared square root x divided by 2x, which would give us 3x square root x, which would be, so 3 over 2 actually, and this would be 1 plus a half. So this would be, so this would actually be, we'll combine these two variables, so we would end up with x 3 over 2. So we can see that this does not equal this. So we can see that the exponent here and this exponent is not true, so this is not equal. And we know that this does not hold true. Another way to think about why this statement is false is as follows. Let me clear the board over here. So what we can think about here is if we just took the derivative, so of f prime at x. So if we took the derivative of this, we know it would be, so sorry, if we took the derivative of f at x, we know that would be the derivative of the function square root of x, so the derivative of this multiplied by the inside. So we usually what we do here is the derivative of the outside, so f prime at x, f prime at square root x, and then the derivative of the inside, which would be 2 square root x. Or to make it a little simpler or easier to understand, it will be multiplied by 1 over 2 square root x. So if we had, so the derivative of this would just be a half x minus 2, which would give us this. And then we can see here that the top, the numerator, should not have been f prime at x, but it should have been f prime square root of x, because usually when you're taking the derivative of a function within a function, what you should be doing is the derivative of the outside function divided by the derivative of the inside function. So, and that's kind of another way of thinking about why this statement is false. So part A, we know is false. So we'll look over here. Let's go through quickly what the junior tutor said for part A. So 6a, the given function is blank. So here there's no real, there's a lot of gaps in the solution. Seems like there was an error translating the solution into OneClass's website. So there's no real solution. Similarly for B, let's go through B actually. Okay, so statement A is false. Let's look at statement B. So here it's saying if a circle is expanding and its radius is increasing at a constant rate of 2 centimeters per second, then its area is increasing at a constant rate. Note that area is this, true or false. So is this true? So if the radius is increasing at a constant rate of 2 centimeters per second, does it mean that the area is also increasing at a constant rate? So we'll write out some equations to figure out how to think about this. So the first equation is just the one given over here, area. So this is question number 1. This is the first question we're going through, part B. So area equals pi r squared. And essentially what we're saying is the radius is increasing per some unit of time. So we could represent r as the following. So we could say r is some constant times t, where t is just time in seconds and is multiplied by a constant. This is an equation for, you can kind of also think of the simple format, which is y equals mx plus b. So here r is our y and x is our t, and we can see that this is a linear equation, and the rate is increasing at a constant rate. So we could substitute for c equals to 2, or any rate, it won't really matter, but we'll define it as such. And let's think about let's substitute this in and see what happens to the area over here. So if we substitute it in, we would get area is pi ct all squared, which would give us pi c squared t squared. So here we know that the beginning terms, these are just constants, so we just some number if we were calculating it, and t here is our variable, which is squared. So right away we can say that because t is squared, it would not be increasing at a constant rate. So area would not be increasing at a constant rate because its equation here is raised to the power of 2. So it would be in a plot, it would look something like that, versus CT would look something like this, and constant rate is this. So here once again, if we think of y equals mx plus b, so m is our constant here, plus b, x is just t, a is just y, and here we know that x is raised to the 1. This is the linear equation. Since t is squared, it's not a linear rate, so it's not increasing at a constant rate. And we can say that area is not increasing at a constant rate. So we can also say for b, the answer is false. So let's go through with the junior 2D set. So the given function is f at x, which is differentiable. So for a, we already said that didn't really make much sense. So for b, if the radius of the circle is increasing at a constant rate, its area is increasing at a constant rate. False reason. The area of a circle. So we're present. Okay, so this is an incomplete answer to the question, but we went through the question step by step, and we know that both statements are false. So we'll say incomplete answer. Both statements are false. Excuse me. Okay, so yeah, we'll mark this as incorrect, and we'll move on to the next question. Okay, so there's no question here, so I'm just gonna look at the solution, or just hover over this. So here on top, by hovering over here, the question is, how do you find the square root of 49? And it looks like this question is asking, how do you find the square root of 49? So before I do that, there's question number 2, and we're asked the square root of 49. So this is a kind of one of the square roots that should mostly be memorized. So this is not really a square root that you can kind of multiply out. Like if you had, like, let's say a bigger number like 1600, let's say you wanted to find the square root of 1600. Here you would look for things that 1600 is divisible not by, like 100, and then you would simplify it out. Here for 49, there isn't much that it's divisible by other than essentially 1, 7, and 49. So because we know it's divisible by 7, it would be 7 times 7. So 7 times 7 gives you 49. So this is a matter of just knowing your multiplication tables. And you know that the square root of 49 is 7. So let's go through with the junior 2D set. So the square root of a number n is the number which when multiplied by itself gives the number n. So yeah, so when we multiply 7 by itself, we get the square root 7. So this is for any number. So let's say we had 36. What is the square root of 36? So we know 6 times 6 is 36. So we put that under the bracket, and since we're multiplying 6 by itself, we know the answer is 6. And the solution goes on to say the square root of 49 can be calculated taking out factors of numbers as shown, and goes through an example or the process of how to get that. And the square root of 49 is plus or minus 7. So usually when you are using a square root in solutions, when you're solving, you would say that the solution is plus or minus 7. So if you had like some kind of function and you had to figure out the square root of 49 and it was one of the roots, then you'd say the roots is at plus and minus 7, so you'd have two roots. So here there's another example. So this example will show you what I mean when you think of what are things divisible by. So what is the number divisible by? So let's go through that one. So we'll erase all this. Okay. So we have the square root of 196. So we can see here that the junior tutor can essentially divided by 2 twice, got to 49. We already figured out what the square root of 49 is 7, divided by 7, and ended up with the final answer over here. So here, if we look at this, we know that if we divided by 2, if we divide 196 by 2, we get 98 times 2. And then let's say, so 196 is equal to 98 times 2. And we can take this even further and divide 98 by 2 again. So the reason you divide by 2 is because we look at the last number and we know 6 is divisible by 2. That means this whole number can be divided by 2 with no remainders. So we know 98 divided by 2 is 49. So we'll have 49 times 2 times 2. So these two are equivalent to one another. And we'll go on because we know 49, as we solved above, is sorry, give me 1 second. Let me move this out of the way. Alright, so we know 7 times 7 times 7 is 49, and then we have the times 2 times 2. So knowing this, we know that we can split this up into 2 square roots. So we have 7 squared and then square root of 2 squared. So we'll end up with 7 times 2, and this is a simplified form that we can use. So we know right away that this is 14. So because usually we memorize multiplication tables up to 12 times 12, so 196 might be a little more difficult to think what the square root of that is. This is a way to derive kind of what the square root of this, and we know it's 14. So 14 squared is 196. And once again, we add the plus or minus. Another example that the junior tutor goes through is the square root of 9. So this is also a pretty straightforward one. Okay, so we'll mark this solution as correct. So great job. Correct answer. Okay, let's move on to the next question. Okay, so this is question number 3. Okay, so the question is asking, how do you find the cumulative relative frequency? So let's go through what the junior tutor had for the solution, and then we'll go through how to get the correct answer. So a frequency, reading over here, a frequency is the number of times a given datum occurs in a data set, and then we're looking for the cumulative relative frequency. So we're defining relative frequency, which is the fraction of times a frequency occurs. To find relative frequencies, divide each frequency by a total number of students. So we're gonna go through this process down here. So cumulative relative frequency is the accumulation of previous relative frequencies. So we're calculating each relative frequency for each kind of data set, and then we're adding the accumulation. And then to find the cumulative relative frequencies, add all the previous relative frequencies to the relative frequency for the current row. So let's look at the table, because that might have not made much sense, but we'll look at this table to understand what's going on. So here, this is kind of the given table for this example. So the data 3, 5, 2, 7. So this is For each data set here, we have the frequency 20, so it's occurring 20 times. For a data 3, 12 for 5, 14 for 2, and 4 for 7. So in the above table, data is given in which 20 students study 3 hours. So there's 20, the number of students that study 3 hours. So here data is representing for how many hours each student is studying. We have 12 students that are studying for 5, 14 for 2, and 4 for 7. In the table below, table 2, we're calculating relative frequency and cumulative relative frequency. So here we can see that we start off with 20. We do 20 times divided by 50. So 50 is here is adding up all these numbers. So we have 20 plus 12 plus 14 plus 4, and that would be 50. So 20 plus 12 is 32. 32 plus 14 is 46, and then 46 plus 4 is 50. You can also plug this into your calculator to verify. So here we take the frequency divided by the total, and we end up with 0.4. And then for the first row, the cumulative relative frequency was just 0.4. Moving onward, we do the same thing for the second row, and then the cumulative relative frequency here is a little different because we have to take the previous one and add it to the current one. So we add these two and we get the cumulative. And then the next row, we take essentially all 3 rows and add them up, or we take the solution from the second row and add it to the frequency of the third row. And then lastly, a similar idea, it will be just adding all of these up and you get 0.64. So, or you can add 0.56 plus 0.8. So this should be 0.8 actually. And then this is kind of the example that it shows you. So essentially for any data set, this is the process that you do. So let's run through this table doing the calculations just so you have a better grasp of what's going on. So if we had, so we have for row 1, so we'll say data, and then we have frequency, and then we have relative frequency, and then we have cumulative relative frequency. We have 3, 5, 2, 7, and then we'll do this. And then so for the frequency of 20, 12, 14, and 4. So if you were given this in a question, you would be given this information right here, and you would need to go through how to calculate the relative frequency and the cumulative relative frequency, and you would have to try to figure that out. So here we're let's go through the definitions again. So relative frequency is the fraction of times a frequency occurs. To find the relative frequency, divide each frequency by the total number of students, and that's what we're going to do. So we know the total is 50. We'll take for the first relative frequency, we take 20 divided by 50, and that will give us 0.4. So we double check, put this in our calculator, we get 0.4. And then next we'd have 12 divided by 50, so we'll plug it in just to double check the calculation. We'd get 0.24. And then we have 14 divided by 50. For the third row we get 0.28. And then finally we have 4 divided by 50. And we get 0.08. So actually we can see that the final row here is incorrect. However, when they're doing the calculation, they get the correct final answer, but this should be 0.08. And then we'll do the cumulative relative frequency. Cumulative relative frequency. So the first one is 0.4, pretty straightforward. The second one is 0.4 plus 0.24, which is 0.28. The third row is 0.28 plus 0.28, which is 0.56. So if you plug that into your calculator, you would get the same, 0.56, that's correct. And then finally, 0.56 plus 0.08, you would get 0.64. And that's how you calculate the cumulative relative frequency. So we'll mark this answer as correct. So Great work. Answer explanation. Great job. Final row should have a relative frequency of 0.08 in the calculation. And we'll mark this as correct. Let's move on to the next question. This is question number 4. So here we're asked, can standard deviation ever be negative? So let's go through what the junior tutor answered, and we'll figure out whether or not standard deviation can be negative and how we can go about getting the correct answer. So the standard deviation is the quantity which shows how much a value deviates, varies, or disperses from its mean value. So if we had a data set of values, the standard deviation is telling us how much does this do these values deviate from the mean, or one value deviates from the mean. For a measurable quantity x, if the mean value is known and is denoted by x bar, then deviation of the measured quantity is written as d equals x minus x bar. So measurable quantity x, some value in the data set, if the mean value is known and is denoted by x bar, so x bar is the mean, the deviation is the actual value minus the mean value, and that's how you get the standard deviation. So the standard deviation is then written as the square root of the average of the square of deviations as given below. So here you do the summation of all the deviations for each data set, and you'd square them, and then it would give you your standard deviation. Since n is the number of samples, therefore the term inside summation cannot be negative. So n here is just how many data points you have, or the total number of samples. And it's saying because n is the number of samples, therefore the term inside the summation, so this term over here, cannot be a negative value. Also, by definition, standard deviation is taken as a quantity always, since it shows deviation of measured quantity, which is required to be a negative value. Yep. Okay, hence the value of the standard deviation cannot be a negative number. It is either 0 or a positive value. So essentially what we're saying here is because n is a positive number, it's based on the samples. We can see from this equation for standard deviation, there's no scenario where we could actually end up with a positive result, because n will be positive and this is squared, so we'll actually end up being positive. Another thing you should know for standard deviation is that whenever we have essentially as soon as you have two different, or at least two different numbers in a set, that are not equal to one another, then the standard deviation will be greater than 0, so it will be positive. So this is also another general rule. So for essentially all data sets, we'll always end up having a standard deviation that is positive. So can standard deviation ever be negative? The answer is no. And we can also kind of use the equation over here for standard deviation to answer the question. So we'll mark this answer as correct. And we'll move on to the next question. So this question is more of a, I guess, knowledge-based question, and sometimes just kind of using this equation to think about why standard deviation can be negative. You can also kind of just think about it in general terms. What does standard deviation represent? And that can also kind of help you think about this question. So I'll mark this as correct. So the next question, we have question number 5. Okay, so we're asked here, draw the graph of the trig functions y equals sine squared x and y equals sine cubed x. So the junior tutor has the following answer, and then we'll go through how to get about the correct answer. So we have these two functions. The trig functions are the periodic functions with a period of and the period of sine x is 2 pi. So for sine x, we know that the period, so we'll say period is 2 pi. Period represented by t. The value of sine x is equal to 0 when x is equal to plus or minus n times pi. So we can see at 0, so when n is equal to 0, we have, when x is equal to 0, we have 0, and then when we have n, so 1, we have at pi, so 3.14 over here, x will also be 0, and so on. So sine x, will also be 0, and so on. As we know, the value of sine x lies between -1 and +1. So for sine x, we know that's between -1 and +1. Here, sine squared x is greater or equal to sine cubed x for this interval, in the interval when sine x is positive. And then they plot the two graphs. So one way to plot these two functions is to kind of just substitute for, let's say, 1, 2, 3, 4, and so on, and kind of just draw dots. You can also cut it down even further. This is kind of the simplest way to go about drawing the graphs. You can also kind of plot it using a graphing kind of calculator, or so as they did here, they kind of just use an online website to graph them. So we'll try to explain what does sine squared x and sine cubed x look like. So sine squared x, so we know for this the period is also 2 pi. So based on this plot, we'll look at this plot. So we have the from 0 to 2 pi. Actually, if we have here to 0, so actually let me double check something over here. Okay, so actually, it would be actually just pi. I was thinking of something else. So here we can see from the plot, because from 0 to 3.14, this section of sine squared x is repeating over and over. So we know this is the period. And then for sine cubed x, we can see from the plot between pi and negative pi, so we have 2 pi, so pi over here and negative pi, so we have 2 pi for the period. So let me just double check that again. Yep. So we have here that these are the periods, and then We can see that here we're claiming that sine squared x is greater than or equal to sine cubed x. So based on this graph, but if we were asked if sine squared x is greater, like is this statement true? Like if we're asked is this statement true? To know if it's true, we could just plug in a value that's over here. So if we know that the period is pi, we can plug in pi divided by 3. We know at this point these two graphs are equal, but at this point they're not. So if we look at the third, so at this point this is about pi over 3. So if we set sine squared at pi over 3, and we had sine cubed at pi over 3, we know for sine squared pi over 3, if you plug this into your calculator, you get 0.75, and then for sine cubed pi over 3, you get 0.64. So this is just kind of just plugging in values. You can see that sine squared is greater than sine cubed, and then by using a graphing calculator or some kind of graphing software, we can see visibly what this looks like. So in a situation you usually would not be asked to draw it completely. You kind of just have to infer these like plug in a couple of values, and you'll get the sense because it's a sine function, it's repeating, so you can think about what the period is and repeat it based on that, and you can also plug in values as such to know which function is greater or less than. So we're gonna mark this question as correct. So correct answer. Great job. Okay. So question number 6. Okay, so for this question, we're asked a rectangular storage container with an open top is to have a volume of 8 cubic meters. The length of its base is twice the width. Material from the base costs $4.50 per square meter. The material for sides is $6 per square meter. Find the cost of the material for the cheapest such container. And we're given an image. We'll open this up. So this is just the question again. So let's just close that. So let's go through what the junior tutor said. Here the surface area has to be optimized. So this is an optimization question. While the volume is kept constant, length is 2 times the breadth. The breadth is x, and so on. So now they have kind of missing words in between this. So this isn't really a full solution. And it doesn't look like they give the correct answer at the end. So we'll go through step by step how to obtain the correct answer for this problem. So this is question number 6. So the first thing we want to do is just kind of write down some givens. So we know that the volume will be 8 meters cubed. So we have 8 cubic meters. We can draw kind of the picture of what this box looks like. So we have some box as such. So something like this with, let's say we have here the length of its base is twice the width. So if we have L over here and W over here, and we have H over here, and we know that there's an open top, so there's no material in the top area. So this area there's no material, it's just open. And then material for the base costs $4.50 per square meter. So we can say for base is $4.50. And for sides, I believe for the sides, we'll represent that by S, is $6. So 6. find the cost of material for the cheapest. So we're trying to look for the minimum. We're trying to find some function and look for the minimum. So we know we can start off by saying volume. So the volume of this container would just be length, width. So length times width times height. And then the next thing that we can define is based on this statement. The length of its base is twice the width. So if we did 2 times the width, we'd end up with the length. So we could say length is equals to 2w. And we'll substitute this into this equation. So we'll say this would give us the volume, which we know is 8 from above. This is given in the question, which will equal L, which we know is 2w, times w, the width, times the height. This will be 8 equals 2w squared times height. We'll isolate this for height, so we know height is equal to 4 divided by w squared. Okay. So we'll keep this in mind. So let me just erase some stuff to make some space. So we've figured out how to derive this. And we'll erase this. Okay. I'm going to take this and move it up here because it will be useful to us later. Okay, the next thing we want to do is define a cost function. So let's say cost, we'll represent that by C, will be equal to 450. We know that's the cost for the base. 450 times the area of the base. So we represented the area of the base with L and W from our diagram. So we'll redraw the diagram again. So we had something like this. And like that, we had W and L and then H. So we have LW. So that's all we need. We know that the top is open. And then we add the 6 for all the sides. So we need an equation to represent the area of all the sides. So we'd have 2WH plus 2LH. So this side and the back side is represented by WH times 2 because there's 2 sides, and then this side and the back side of that, or the opposite side, is L times H, which gives us 2LH because there's 2 sides of that. So this is our cost equation. Now we're going to substitute in some things that we already know. We know this and we know this. So we're going to substitute H and L to get all this equation into the format where C is represented by W, which is the width of this box. So the variable W. So we'll say C at W will equal 450 times 2W, so that's for L, times W plus 6. And then we have in brackets 2W, so W you'll say the same, H, which is up here, 4 divided by W squared, 4 divided by W squared, plus 2L, which is 2W, 2W times H, which is 4 divided by W squared, in brackets. So we'll keep going with this. So we have 450 times 2, which is 9. W times W, which is W squared. And then we have plus. So we have the 6 in front. We'll keep that in front for a second here. And we'll look at inside the bracket. So we have 2 times 4, this is 8. And then we have W divided by W squared, which is just divided by W. And then we have 2 times 2 times 4. So 2 times 2 is 4. 4 times 4 is 16. So we have 16. And then similarly, W divided by W squared. So we have divided by W. and this will give us 9w squared plus, so 6 times 8, so 8 plus 8 is 16. 16 times 2 is 32, and then adding 16 again to that, we would end up with 48. So for the first one, we have 48 divided by w. And then 6 times 16, so 6 times 16, we end up with 96. So actually we can add these two together. So 96 plus 48 gives us 144. So we'll erase that. And we'll write it all together as 144. Oh, whoops. That didn't work as I intended. 144. And that is our cost function. So from here we want to take the derivative. We can also write this as follows. So we're going to take this bottom out and we're going to write it in this format so we can make the derivative easier. So we'll erase some space up top. So really, we only really care about the final equation. Okay. So this is CW. So we take the derivative of this function and we set that derivative to 0 to find any maximums or minimums. So the derivative of the function below is 18. One second. So 18 w plus, so this is actually -1 over here. I erased that accidentally. So we'd have actually not plus, so we'd actually have minus. So we have minus 144 w to -2. So setting this to 0, we'd have 18 w minus 144 over w squared. This would give us 144 on the left side divided by w squared, which would give us equal to 18w. So we'll divide both sides by 18 and we'll multiply both sides by w squared. So we'll end up with 144 divided by 18 is equal to w cubed. Therefore we know that the cube root of 144 over 8. So I wonder if this divides out visibly. Yep, so this is 18. So 144 divided by 18. 144 divided by 18 is 8, sorry. So yes, and then we get w is equal to 2. So we know 2 times 2 times 2 will give us 8. So 2 times 2 is 4, times 2 is 8. So the cubed root of, so we'd have this, and the cubed root of 8 would just be 2. So we know that the width is 2. So we'll just double check that math. Yep, that's correct. And now we can take the second derivative and plug in 2 to verify that this is a minimum. So the second derivative of this function is 18 minus plus, 288 w to the -3. And if we plugged in 2, so if we said the second derivative of that function and we sub in 2, we would end up with 18 plus 288 divided by the cubed root of 2, and this would be a positive value. So the actual value is 246, but all we really need to care about is that this value is positive. So this is greater than 0. This means that at w equals 2, a minimum exists. So let me just double check something here. Just give me a second here. Just trying to figure out what's went wrong with the camera. Okay, there we go. Sorry about that. My camera was not functioning properly. Okay, so let's get back to the question. So we had, we completed the calculation, took the second derivative. We ended up with the second derivative is greater than 0. So therefore we have a minimum, and we know we've minimized the cost function. So at the width equal to 2 meters, we know that the minimum exists. So we'll clear the board for a second here. So we know at w equals 2, the minimum exists. We can also calculate, so we're actually here asked to find the cost of the material for the cheapest such container. So all we really need to do now is just plug it in back to the original equation. So at c equals to 2. So let me rewrite the cost function that we originally defined. So here we would have 9w squared plus 144 divided by w. So we'll substitute at c equal to 2. We have 9, 2 squared plus 144 divided by 2. So we get 9 times 4, which is 36, plus 144 divided by 2, which is 72. And 36 plus 72 gives us 108. So here we have dollars. So the minimum cost would be $108. We can also figure out what the other lengths are, but here we're not really asked for the other lengths. We're only really asked for finding the cost of the material for the cheapest container. So this is the final answer for the question. So the solution provided by the junior tutor is incomplete because there is missing values, so I'll mark this as incomplete solution. Answer is the minimum cost that can be obtained is $108, and we'll mark this as incorrect. Okay, so the next question that we're asked over here is what is 0.625 as a fraction in simplest form? So whenever we're looking at a number like this, I would start off by just writing it over like a very large number, so 0.65. This is question number 7. So 0.625. We know that's equivalent to 625 over 1,000. So basically you count how many decimal places over, so 1, 2, 3, and then you know that there's 3 zeros in the bottom of the fraction, so we'd say 625 over 1,000. And then here we can divide by things that are divisible by 625 and 1,000. So right away I see this 25 over here, and there's 600. So I know for 100 is divisible by 25 for sure. That means 600 is also divisible by 25. That means also 625 should be divisible by 25. And we know 1,000 is also divisible by 25. So if we divided by both top and bottom by 25, we would end up with 25 over 40. So 25 times 25 is 625, and 25 times 40. So you can either use this, use a calculator to calculate this, or just use mental math. And then you can divide this by 5 again. So we'll divide top and bottom by 5. So 5 divided by 5 is just 5. 40 divided by 5 is 8. And now we can see that the numerator and denominator don't have any more numbers that are divisible by both. Therefore, we've obtained the fraction for 0.625 in its simplest form. So let's look at what the junior tutor said over here. So a fraction is constant math. So they describe what the fraction is. The decimal value is given in a question, can be converted. So really here's what is the important part. So you start off with 625 divided by 1,000, because you have decimals in the 10th, 100th, and thousandths position. So 625 divided by 1,000 divided by 25 bottom and top, and they go through the same process to get 5 over 8. So this answer is correct. So correct answer. Great job. And we'll mark this question as correct. Okay, so question number 8 over here is using the quotient rule. So we'll leave this question actually for the next session. Okay, so thanks for tuning in into this session. Hopefully you found this session helpful, and you found the math problems that we went through had clear solutions. If you have any more homework, if you need any more homework help or tutoring, you can always visit the OneClass website, or you can visit the link in the description. You can also subscribe to the OneClass YouTube channel to watch more videos like these. I'll see you in the next session. Goodbye for now.